Hi, welcome to this lesson on error detection, and this is Rajmati here. So I'm going to be your guide throughout this lesson. So we have learned about data transmission, how information moves from one device to another. So today we're going to look at error detection. So first of all, why do we need error detection? When data has been transmitted from a sender to a receiver, there's a risk the data has been corrupted or changed in some way. So as you can see, we have a sender and then a receiver. We're sending information. Now, data may be corrupted, changed in some way when it is transmitted, and this can occur whether the data is transmitted over short distance or long distances. Now, errors may happen, maybe a few bits may be changed, or there are some transmission errors like we have seen when data is transmitted through light pulses or radio waves. So there is a need for error checking, which is very important, and in this lesson we're going to learn about the different methods of error detection. Now, it may happen that we are sending file as a sender to a receiver, and it may happen that the file is corrupted, or maybe it has been hacked in some way, and it is very important that we have some form of error detection techniques. And there are several methods of error detection depending on what kind of errors we want to detect, and some of them, they do have some shortcomings. And for the exam, you must be able to analyze the differences between the different error detection techniques. So some of the methods to detect errors are parity checking, automatic repeat requests, CHECKSUM, and echo check. In this lesson, we're going to look at parity checking mostly, or parity check method. So let's take a look to parity checking now. It is one of the methods used to check whether data has been changed or corrupted following transmission from one device to another. So as you can see here, I have a sequence of bits, or we can say a packet of information, or some sort of information that I'm sending, and this information have a series of bits 110, 1100. Now, this byte of data must have an extra bit allocated to it known as a parity bit. Now, the parity bit can be either a 0 or 1 that I'm going to add. So before sending the packet of data or the byte of data, one extra bit is added, and depending on the scheme I'm using, even or odd, I'm going to add a 0 or 1. Now, systems that use even parity have an even number of 1 bits, and systems that use odd parity have an odd number of 1 bits. So if I'm using even parity, there must be an even number of 1. So when you're counting the number 1, it must give an even number. And if you're using odd parity, when you're counting the odd number of ones, you must have an odd number. And we know that an even number is one that is exactly divisible by 2. That is, let's take for example 4. 4 is exactly divisible by 2. Now, let's see this byte now, 1101100. Now, as you can see, we count the number of 1. So 1, 2, 3, 4. We have 4 ones. Now, if I'm using even parity, the number of ones should be even. But if I add a 1, it's going to be odd, that is 5. Therefore, I add a 0, so that when I count the number of ones, that is going to be 4. So if this byte is using even parity, then the parity bits needs to be 0, since there is already an even number of 1 bits, in this case 4. So If I count the number of ones here, we have 4 ones. And since I have 4 ones, we know that it's already even, therefore we add 0. If I add a 1, it's going to be odd, therefore it's better to add a 0. Then you can recount the number of ones, it's going to give you even. Now consider the same byte of data. Now if I'm using odd parity, so you first count the number 1, so we have 1 1 1 1, so there's 4 ones here. So since I'm going to use odd parity, the number of ones must be odd. That is, it must not be 4, it must be 5. Therefore I add a 1 to make it an odd parity. So parity byte, or let's say parity bit itself, is a method where we add 1 extra bit. Now if you take a look to this exercise, if I have 1 1 0 1 1 0 1, okay, in this case, since I'm using even parity, okay, so the number of ones here is odd, obviously. Therefore in this case I will need to add a 1 to make it even. So if you count the number ones, I'll repeat it again. If you count the number 1, it's 5 ones. 5 is an odd number. I need to make it an even, so I add 1 to it. Okay, we can obviously attempt the other principle to add parity bit to the second one. So since it is even parity, you can see the number of ones are even, therefore I need to add a 0. So there are 4 ones, I can't add a 1 here, therefore I add a 0. If I add a 1, it's going to be odd, therefore I add a 0 to it. So if you look at the third example now, I'm using again even parity. The number of bits containing 1 is 3, so there are 3 1 bits. So if I'm using even parity, I need to add a 1 to it. Okay, now if you count the number of ones, you're going to say it's 4. Let's take a look to the fourth example now, which is odd parity I'm using. So 1 2 3 4, there are 4 ones, so I need to convert it to an odd parity bit. So in this case I will add a 1 so that the number of ones become odd, which is 5. Let's come to the fifth example now. Okay, we are using odd parity again, and the number of ones, if you count, is we have 5 ones, so it's already odd, therefore I will need to add a 0, obviously, to make it odd number of ones. So these are some of the examples of exercises that you may have when it comes to parity bit. You may be given a register and then asked to add an extra bit to it. Now sometimes you may be asked following a transmission whether the bits have been transferred correctly or not. So you can take a look to other past exam exercises. It will be helpful. Now let's take a look to protocol. Before data is transmitted, an agreement must be made between sender and receiver regarding which of the two types of parity we are going to use. For example, if we are going to use even parity, the data or the byte when it has received, it must contain an even number of ones. If there is no even number of ones, therefore there must have been an error somewhere. So let's see how error is normally detected at the receiving end. If a byte has been transmitted from A to B and even parity is used, an error would be flagged if the byte now have an odd number of ones bits at the receiver's end, like I've said earlier. So for example, let's take a look. If even parity has been used, So I know the number of ones must be even. So if I count the number of ones here, so I have 1, 2, 3, 4, 5, 6. So therefore, since even parity has been used, byte looks correct with no errors. Now let's say if this was not a 1 and this was 0, and I'm again using the protocol even protocol. Therefore, if I count the number of ones, in this case, that will give me 1, 2, 3, 4, 5. Therefore, in this case, I know there must be some, there has been some errors, or the data is corrupted, depending on which protocol I've used. So even protocol ensures that the byte that has been received at the receiver end must contain even number of ones. In the same way, if you're using odd parity protocol, you have to count the number of ones, and if the number of ones are not odd, therefore there has been some correction. Obviously there are some shortcomings when it comes to this protocol. And it's very important that we analyze each of these error detection methods. Now let's take a look at an evaluation. We have a series of bytes here, and we're supposed to take a look which of the following have an error. So the first one, you can see that we're using even, second one even, third one even, and then odd. Okay, so if you take a look for the first one, we're using even parity. So the number of ones here are 1, 2, 3, 4, 5, and 6. So there are 6 ones, and even parity has been used. Therefore, you think it's correct in this case? Yes, since it is even parity, this byte is correct. Now the second one, we're using even parity again. So if you count the number of ones, 1, 2, 3, 4, 5. So since it is even and 5 is not an even number, we understand that this byte here have been transmitted incorrectly. For the third one, I'm again using even parity, and in this case, since I'm using even parity, you can just count the number of ones here. So I have 1, 2, 3, so 3 ones. 3 is an odd number, therefore this byte has been transmitted incorrectly. For the fourth one, I'm using odd parity, and there are 5 ones, so 5 is an odd number, therefore it has been transmitted correctly. For the fifth one, so 1, 2, 3, I think I have 6 ones here, and I'm using odd parity, therefore it has been transmitted incorrectly. That is, the byte is corrupted. Okay, let's take a look to the concept of parity blocks, and it's a very important concept when it comes to CIE computer science O level. So you're given a block of bytes here, and you're supposed to identify which bit or byte has been corrupted. So as you know, there are certain shortcomings when it comes to parity checking. When 2 bit has been flipped, obviously it becomes very difficult to analyze and detect errors. Now, when it comes to parity blocks, you will need to count the number of ones by rows and by columns, and then you'll have a point of intersection, like you can see in this diagram here. So for bit 5, as you can see, and byte 8, it should be a 0. And if you count at bit 5, the column bit 5, 1, 2, 3, 4, 5, so there are 5 ones. And byte 8, 1, 2, 3, there are 5 ones. In this case, since I'm using even parity, it is obviously at the point of intersection, it is supposed to be a 0. Okay, so let me use a screen annotation. So I'm using even parity here, checking method of the even protocol. If you count the number ones for each of these bytes, as you can see from my screen, okay, in this case there are 5 ones. Sorry, there are 6 ones for the first one, and for the second one I have again 4, which is even, so that's correct. For the third one, if you count, we have 1, 2, 3, 4, 5, 6, again it's even. Byte 4 we have 2 ones, which is correct. So you're going to do for each one of them, and maybe draw a line here at byte or at bit 5, okay, and for bit 8 also you're going to draw a line, and same for bit 5, which contains an error. You're going to have a point of intersection, and you're going to say this is supposed to be not 1 but 0. So this is longitudinal parity checking. Sometimes we do have question, and it's very important that we do practice question for this part. There are some shortcomings with parity check, or problems with parity check. If 2 bits have been flipped, errors can't be detected. I've already shown you how. If 2 of the bits are flipped, what is going to happen? The protocol for even and odd parity is not going to work.